It's no argument about the effect. Up in Everest Base Camp, it's obvious, if you understand the physics or physical chemistry, that the water will boil at a lower temperature. Now, the problem is exactly how much lower the boiling point will be.
I've got the Katmandu thermometer and our lab thermocouple, and at present, what's that reading there? The temperature in the kettle is at 12 degrees C, and the thermocouple is reading 14.
The first problem is that Brady's thermometer is slightly dodgy, and particularly worrying is if you watch his video, they measure the temperature of a frozen lake, which should read 0 degrees centigrade, and they get a temperature of -4.
Is that exactly -4?
Now, this could be because the thermometer was not very good, or it could be that the water in the lake wasn't very clean.
It's now reading 110, and the thermocouple is reading 100.1. So there's a difference currently. Oh, now it's dropping back down. There's a difference of 9 degrees.
But now let's look at the kettle. It's a bit dirty inside, so when they boil the water, it may not have been absolutely pure, which could have meant the boiling point was a bit higher than it should have been. Also not very good for drinking, but it seems to be okay for drinking because Brady is here back safely. But the second thing is that once it's boiling, they have to stick in the thermometer and read it. And when it was cold and windy, they may not have always stuck the thermometer in at the same depth. So the readings may not have been completely consistent. But having said all of that, if I'd been doing the experiment and it had been cold and windy, I probably wouldn't have done it any better. If you put water under a vacuum, that is, you start pumping out the air above the water, nothing much will happen until the vapor pressure of the water is equal to the pressure inside your vessel, and then it'll start boiling at room temperature. And in fact, if you're lucky, because when water boils, it takes heat out of the water, you can actually start freezing the water solid just by pumping on it. Some of my students are looking at reactions in water at higher temperatures, above the boiling point. This is rather like doing reactions in a pressure cooker, which people use for cooking food very quickly, but we're going to much higher pressures. And our equipment will go up to pressures of several hundred atmospheres, which allows us to take water right up to a temperature of 374 degrees centigrade without boiling. So you might ask, why 374, and how I can be so certain that it's precisely 374. And the reason is that as you heat the water up, the liquid water expands, and the water vapor, because it's at higher pressure, is denser. So the liquid becomes less dense, the vapor becomes denser, and at 374 degrees, the density of the gas and the liquid become the same. And so above that temperature, all you can have is highly compressed steam, and you cannot have liquid water. This is called the critical point. And above that temperature, water is so-called supercritical.